All right, happy Tuesday. How's everyone doing? Great. Well, it's nice seeing all of you. The transition back from break is always a thing, so take care of yourself. Yeah, at least the weather is nice. I think, yeah, this week is going to be amazing weather. So your opportunity cost for being inside is very high. Econ reference, anyone? Yeah, I was talking to someone over break, talking about break and then the end of break. And I was sort of saying, like coming back from break is always like a transition. Being somewhere sunny like I was, it's hard to transition, but I was explaining, like, I love my life. I love doing what I do. I love being here with you all. So there's always a bit of transition, but it's also nice, very nice being here with you all. So break is a good time to remember how amazing it is we get to do this. So yeah, welcome back. Anyone go somewhere sunny? Yeah. Do you think you were the furthest? How many of you think you were the furthest away from Pittsburgh? I was in Arizona. Anyone further away than Arizona? Yeah. Where was that? Where was it? Where's that? Oh, I had someone in one of my other classes who was there too. That's nice. I think Arizona's still further away than Dominican Republic. Yeah.
I don't know if Arizona's farther, but I was in Aruba.
Um,
Right above Venezuela.
I think that's probably further. Yeah. We could look it up on a map. We know how to compute distances, right? Using latitude and longitude. So someone could do that.
Yeah, where in Arizona were you?
Tucson. Yeah, someone figured that out. Whether Aruba is further away than Tucson. Okay, well, so we have maybe a bit of housekeeping to do before we get in. Just first off, it's nice seeing all of you. I love what we're doing, break is always a good reminder that what we do here is just pretty amazing. So a bit of housekeeping. We're going to start part 4 today. So we're going to talk about where we've been in this semester and then what it is we're trying to do with part 4. And then I have a couple of things about the assessments coming up. So we don't have a mini exam today, like I mentioned before break, and then also after break, via an announcement. You can also always find the schedule here. So we're in week 10. I haven't posted part 4 yet, but once that goes up, you'll be able to see part 4, week 10 materials. So we do have a mini exam next week. We have a homework that's technically due this week, but because I haven't posted it yet, and you always, no matter when I post it, you get a week. So that's going to go up potentially this afternoon. But of course, you're always going to get a week. So no stress about that. That will go up pretty soon. So I also wanted to talk a bit about the final projects. This is a good time to start thinking about types of research questions you might be interested in. Something with data that you can then apply some of the tools we're developing in this class. So I talked a bit about some of the types of projects students have worked on in the past. And maybe I'll resurface those now that we're getting closer to the time to start thinking about final projects. But I want you to be thinking about something that you can apply statistical tests to. Some data that you might be able to have access to, and that's interesting to you. The first priority for me when thinking about projects is that you pick something that you're interested in. I'm going to post a bit of information about the structure of what I expect, so you can be thinking about how to approach the final project. But first and foremost, I want you to do something to work with data that you have some interest in. And if your research interests, or like the question you might be interested in, doesn't fit perfectly within the structure of what I propose for the final project, then I want you to have a conversation with me, and we can be flexible about the requirements for the class. That's like the main thing for me. I want you to be doing something that you're interested in, and then I can make the course requirements fit that. And if you have like another class that you can overlap with what we're doing in this class, then I would love you to try to overlap two projects. So if you have a class that requires you to work with data, or like write something about something you're interested in, maybe not with data, but you want to bring in a data set and sort of merge two projects, I would love that for you. So what I'm saying is, I want you to do something that's interesting, and I want you to fit the project to what you're interested in. If what you're doing falls outside of what I propose as course, as like a structure requirements, I need to have a conversation with you about it, but I can be very flexible. I just need to know about it. Okay, any questions about that? All right, very nice. So homework, final project, mini exam next week. What we're doing in part 4 builds off of what we did in part 3. So most of the class has already seen this recording, but you'll remember we did an asynchronous class the week before break. So that second class the week before break was asynchronous. And fortunately for you, you can watch these recordings of the lectures at like 1.5 speed. So you don't have to listen to me talk so slowly. I try to speed up my speaking cadence, but I can't always keep up. You're supposed to laugh at this. But you can watch this at 1.5 speed, but you do need to at least go through this material. It's one of the biggest ideas, right? We started off with the central limit theorem and built up the ideas of the t distribution right before we left for break, and then this was essentially hypothesis testing, which is testing whether a mean is equal to some value. And so we're going to talk about one example today, and then we're going to start developing the core idea, the extension of a t-test into what we do in the field. So this is a big one today. This is like, by the end of class, we are going to end up on the the front porch of the big model that we're working with this semester. Okay, so what is it that we've been doing? So you'll remember in part 1, we introduced just like data and working with data, visualizing, summarizing data, particularly univariate data. And for a lot of you, this was the first time you started working with code to interact with data and make visualizations. And so we got started with that. In part 2, we talked about visualizing relationships between variables. So this was like multivariate data, summarizing relationships, time series, these types of things. This is all in the interest of understanding what the data set looks like. And so different visualization techniques were in the interest of understanding what the data was telling us. And different types of questions require different types of visualizations. Different types of data require different types of visualizations. Our eyeballs are just best for understanding relationships. Visualization allows us to quickly understand what's in a data set. But visualization, even though it's the first place to start, doesn't allow us to answer many types of questions. So for example, if I asked you what the price elasticity of demand was, and all you could do was give me a figure, this would not be enough. You couldn't answer for me what the price elasticity of demand was simply using a scatter plot. You could hint or like give an indication of like whether it was positive or negative, but you couldn't tell me what the number was. And often we require a number. So you'll remember from your intro class, we talked about like the slopes of demand curves. If you want to know the slope, or if you need the slope in your demand curve, you have to have a number. You can't insert a scatter plot in for the coefficient, right? So we need some way of establishing what the numbers are. And so what we turned to in part 3 was our statistical models. So we built up these this model of randomness and certainty. And so in part 3, we built this up. And this was the basic idea led us to a t-test, which we're going to talk through at the beginning of class today. But what we're doing in part 4 is taking this idea of a t-test and generalizing it. We have these ideas of like random variation, the central limit theorem telling us that we don't need to know the distribution of the underlying data to be able to say something about the distribution of the sample means, which I always get excited about because it's, I mean, truly one of the most powerful things we've ever discovered, is that we don't need to know the underlying distribution. And we talked about some of the implications. The last class, this asynchronous class, we talked about, we started off reminding ourselves of confidence intervals, sort of a distribution around our hypothesis. And we walked through an example using wait times. So we said, if we have an observed mean, and we want to ask whether it's consistent with a hypothesis. So your boss tells you like, the wait times are 10 minutes, but you see that the wait times in reality in your sample are 10 minutes and 10.85 minutes. You wonder whether the observation is consistent with the hypothesis. And so we walked through this whole thing of checking whether the hypothesis is consistent with the data, or is the data consistent with the hypothesis. Those two questions are mathematically identical. So what we did right before break is we walked through and we set up this distribution centered around the hypothesis, and then we see that there's an observed mean that's pretty far from the hypothesis given the t-distribution that we've established. So we use the standard error of the sample to get us the variability in the t-distribution, which gets very close to a normal distribution when our sample size is large enough. And so we have this distribution. I just randomly sampled a bunch of observations behind the scenes, and then so we wondered essentially like we wanted a way of capturing the level of surprise essentially for this observed mean if the null hypothesis were true. And this is the basic idea with the hypothesis test, which lays the groundwork for everything we're about to do. Hypothesis testing and linear regression, which we're about to turn to, are the same model. Same idea. Which you haven't seen yet, but I'm previewing for you. So we have the null hypothesis and the t-distribution centered on that null hypothesis. And what we did is we walked through the standard deviation to calculate the standard error. And then using the standard error, we constructed the t-distribution. And we were wondering, how likely is it that we would get some event as extreme as what we've seen if the distribution is truly centered on 10? So we saw a 10.85. How likely what's the probability that we would see some extreme event like that? Sort of capturing our level of surprise. And so what we did in one way was calculate the critical regions, sort of the confidence interval around this hypothesis. So these values capture 95% of our certainty around this null hypothesis. And so one way of thinking about this problem, which we often do, is we say, this observed mean falls within this 95% confidence interval, and so we can't quite be sure that it's an unusual event. We're saying it's within 95% of the confidence interval, so it's not so surprising. But if x bar fell outside of this, so it was like 11.5, so maybe out here, then it would definitely be very surprising. So this is one way of thinking about the problem, but often I find this not the most intuitive approach. So what we're going to do today is actually build up a sort of kind of more intuitive approach, which is kind of what it's more of what we use in the field. Okay, so we built this idea, we formalized what we said we called the null hypothesis. So we had a null hypothesis, so the specific value or claim that we were testing, this was like that 10 minutes. We were trying to see if it was consistent with our data. And then we have this alternative hypothesis. It's like the thing we say is true if we reject the null hypothesis. So it's like basically everything that's not the null hypothesis is generally what we claim to be the alternative hypothesis. So it's like, okay, it's just not 10. And so this was sort of what we called the testing approach. How surprising is our data given the null hypothesis? And we can calculate this using a p-value. And so we walked through this idea of using a p-value, which we're going to rely on very heavily to calculate this level of surprise. Okay, so let's say we have this same distribution we've been working with, where we've centered the t-distribution on our null hypothesis. One way of thinking about hypothesis testing is to say, look, we construct the 95% confidence interval, and then if our sample is within that confidence interval, then we fail to reject the null hypothesis. But another way of thinking about hypothesis testing is let's just construct a p-value. We say, what's the probability that we get some value as extreme as the one we see? So not thinking about, rejection regions, just thinking about the p-values themselves. We're going to talk maybe in about a week about, how many of you have heard of p-hacking? P-hacking? Anyone? We're going to talk a little bit about this today, but there's some nuance in this hypothesis testing approach that leads to scientific misuse. We're going to talk about how to, once we understand the testing approach, how to actually be a little bit manipulative in the way we write down our hypothesis tests. And we're going to talk about it a little bit today. But I want you to be thinking critically about whether this kind of approach is actually the right one we should be using as a field. P-hacking is, and we're going to define this later, but I want you to be thinking about how you could manipulate the test itself to get you what you want. So if you want to reject a null hypothesis, be thinking about how you could change the question you're trying to answer so that you do reject the null. In scientific journals at the moment, we see a lot of evidence that's right on the edge of some critical region. So we're, essentially publishing papers that are claiming to show something, but often are not able to be replicated by others. And so part of the problem is actually this testing approach. So we're going to talk about like how to use it effectively, how to use it with integrity, and I'm also going to teach you how to p-hack so that you can get results that are sort of spurious, so that you don't do it. I'm going to teach you how to identify the possibility of p-hacking and how to avoid it for yourself. When we're training ourselves to be ethical scientists and economists, we need to be thinking about ways we can break these models. So anyway, we're going to talk more about this a little bit later, but I just want you to be thinking critically about how we work with these tests. But anyway, so we spend a little bit of time thinking about how to actually calculate p-values. And so what we do, right, is we just look for the area in the tails that's more extreme than the observation we get. So we center the distribution on our null hypothesis, and then we find the areas in both tails. We're going to come back to, I want you to be sitting for a second on this question of why we have both tails and not just the one. Like, I want you to question this. Why is it that we use both tails? We observe just this green region, which is our sample mean. Why do we use both? Why do we have to include this one? So I want you to sit with that for a second. I'm going to ask it directly of you a little bit later, but I want you to think about why. So if the interpretation here is if the null hypothesis is true, then there's a probability of like 7.3% that we, through repeated observation, we end up seeing something as extreme as the sample that we've seen. So it's going to be as far away as x bar is, about 7% of the time. So this should give you some pause for whether the null hypothesis is actually true. If it's that unlikely to see x bar, then maybe the null hypothesis is not so true. So p-values allow us to quantify this level of surprise. Okay. And then we talked about how often we use this cutoff region of 0.05. But I have a lot of skepticism about using this as a formal approach. Because using cutoff regions, just like running a yellow light, you hit the gas right like as the light turns yellow. You try to do everything in your power to not run the red light or not get stuck behind the red light. We have the same idea in sort of the same problem in science. Often, if you're trying to hit some critical region, you're going to do a lot of funny things in your power to end up in a world where you reject the null hypothesis. Okay, so I have the field actually broadly at the moment has a lot of skepticism about this. Okay, so that's the idea. We also talked about the test statistic. We didn't spend a lot of time on this. We're actually not going to spend a ton of time on t-statistics. But if you wanted to calculate the t-statistic, it's sort of a normalized way of measuring the point on the t-distribution that your sample is. Okay, and then we walked through this example, this formal tests. Okay. So that's basically where we left off last time. This time, we're going to work towards a model that allows us to compare between means, what we call a two-sample t-test. How many of you have seen a two-sample t-test before? Yeah, nearly everyone. How many of you could explain to me how it works? Okay, so we're going to remedy this problem. That's the main point of what we're doing today. We're going to, first off, talk about the intuition, how it's related to a single sample t-test. We're going to take two samples and then shoehorn it into a one sample t-test. And then we're going to implement it with code. So no longer, after today, will you be using that chart in the back of your stats book. We're going to eliminate all of that. And in general, you're not even going to use t-statistics for me in this class. You might sometimes, but we're going to focus on p-values. Okay, and then once we get through this today, the first of the generalizations of the t-test, then we're going to extend this basic idea into more complicated tests. So we're starting the progression, complicating our test into much more complicated environments. Okay, any questions before we get in? Very nice. So part 4, we are taking the basic t-test and extending it. So the first thing we're going to do is just remind ourselves of how we construct a one-sample t-test. So this is kind of the last thing we did in the last class. And I'm going to be posting these slides. They're not on part 4 yet. So if you want to follow along, you're going to have to write all the code yourself. But I will post this after class. So feel free to just follow along if you like, or take notes on paper. So this is the thing we did last time, right? So we had our one sample t-test. We had our null hypothesis, which was that the wait times were 10. We had an alternative hypothesis, which was just not 10, so whatever that is. We had this should say 30, so our sample size is 30. Our t-statistic, so we had our sample data here, or sample statistics. So we had a sample mean. This is slightly different than the last example. We had a population mean, so our null hypothesis was 10. And then we had a standard deviation in the data of 1.971. And so all we went through was essentially constructing a one-sample t-test. We're essentially checking the probability under the null hypothesis that we would get data as extreme as what we do. So I have the data loaded here, or the sample data, or the sample stats. We have our sample mean, so this is coming directly from the sample. This is our null hypothesis, so we can maybe just rename this as null. The standard deviation of the data. And then we have our sample size. So I'm just going to run this. And then you'll remember, we walked through and we calculated just the t-statistic directly. So this was essentially what we did here. So we were just plugging in these numbers to get this normalized distribution. We subtract off the population mean, and then we normalize it by the standard error. And this gives us the t-statistic. So all I'm doing here is just writing out the t-statistic. That gives us 2.40. So this is like our sample mean is 2.40 standard errors away from our null hypothesis. That's what this thing is saying. So maybe let's just write this. The sample mean is 2.40 standard errors away from the null. So it's a normalized way of quantifying the sort of distance between our null hypothesis and our observation. So this is nice. I mentioned that we won't spend a ton of time talking about t-values, but when we think about t-values, this is generally how we think about them. Then the next thing we did was calculate a p-value. So we said we want the area using the t-statistic. I mean, it's essentially the area under the curve. I have a nice picture somewhere in here. So it's the area under the curve that's more extreme than the observation we see. And so we walked through how we constructed this using the CDF. So we just construct the CDF using the t-distribution, and then we just multiply it by 2. So this gives us a p-value that looks like this. There's a lot of code here. This is repeat of what we did in the asynchronous class. So if this doesn't feel familiar, take a look at that. So we have a p-value, and I'm looking for someone to tell me how to write out the conclusion here. What is this p-value telling us? Okay, maybe a warm-up question. I want you to write down on your piece of paper. I've constructed the p-value, so no need to worry so much about how we actually write it out, the code. But I want on your piece of paper you to take an attempt at writing out what this p-value tells us. And then I'm going to have you actually refer to your neighbor and check your answer against someone else's. So we're going to take a second here. This is one of the big skills that's required in this class, to be able to take a p-value and say something in English using that p-value. This is not a trivia. This may seem easy, may seem hard. Whether it's easy or hard for you, this is one of the key skills, is taking this number and turning it into something that we can actually deal with. So we'll take maybe a minute here. I want you to write a sentence out on your piece of paper describing what this means, and then chat with someone next to you. Nice. That's perfect. If I heard you correctly.
2.3% chance that we will see a value or our value as far away from the population, or like a value as extreme as ours.
Yeah. Yeah, very nice. Okay, so I've kind of forced you into writing something down. Someone want to give me one possible way of saying a conclusion here? I know Luke's. I heard Luke's, and his is right, so I'm gonna skip his. Appreciate it, respect it. Very nice. Yeah.
Saying we're likely to see a value as or more extreme than the null 2.299% of the time.
Yeah. Yep. So this is like almost perfect. So if I were to summarize this, it would be something like we would see, and this is not exactly how I would say it, but let me just repeat. So this is we would see something as extreme as the null 2.2% of the time. So this is this is like a mathematically equivalent way of stating what you're saying is mathematically correct. We just generally don't think so much about the null being random. We think of the sample being random. So this is a first attempt, and I'm going to write it down, and then I want someone to correct this slightly. But this is mathematically correct, what you've said. So it's something like we would see something as extreme as the null 2.3% of the time. Okay, so this is a first attempt. This is not fully correct, but it's pretty close. Someone want to maybe take a revision at this? First off, let me just say, I love when people give answers that are incorrect or like in the direction of correct. This is a really good thing to do. You don't have to be perfect in this room. You should never try. I don't try. You can see in my slides. My slides are not perfect. Someone want to fix this, make it better. Yeah, Ben. We can talk about acceptance and rejection of the null, but this is not the sort of preferred approach in general. That adds another layer of interpretation on top of what a p-value is telling us. I'm looking for something slightly different. Garrett.
I think something like this. There's a 2.3% chance of getting a sample value that extreme or more extreme from the sample mean or the population mean?
Yeah. Yep. So I would say the null hypothesis at the end. Yeah. So I'm going to write this down, and then we're going to compare these two answers. Turns out they're mathematically equivalent, but this one is the more sort of technically correct interpretation. So I'm going to write this down. So I'm going to revise it just slightly. So under under the null hypothesis, so like assuming that the null hypothesis is true, we would see something as extreme as x bar, our sample mean, 2.3% of the time. So you can see these are very similar interpretations, but this one, and it turns out they're mathematically identical. So we've calculated the probabilities in both of these cases, because we can recenter the distribution either on the sample mean or on the null hypothesis. It turns out that the two numbers would be the same. But to be technically correct, we would write this second one. We're saying, if the null hypothesis is true, how often are we going to see something this extreme or more? That's what this p-value is telling us. So does this look like the null hypothesis is true? If we say we get a p-value that looks like this, does it look like the null hypothesis is true? We're assuming it's true, and then we see something that's very unusual, if it were true. What does that tell us about the truth of our null hypothesis? Yeah.
There's evidence against the null hypothesis.
Yeah. So it looks like the null hypothesis is probably not right, because we're getting something that would be very unusual if it were true. Yeah. So nice. Any questions here? To be able to correctly interpret a p-value is one of the crucial skills in any area of science. Any area of science that requires data, you must be able to interpret a p-value. Okay, so we're going to talk about some other examples. I'm going to have you do this again in a second, but this is good. All right, so any last questions about this example? We're going to do this in a slightly different way to give you a little more practice. This is using sample statistics data. So we have a bunch of data. We have a mean. We have a standard deviation of the sample, and so on. But and this is essentially a restatement of Garrett's conclusion. 2.3% chance of seeing this data or something more extreme, given a true mean of 10. So most of the time, you're not going to be given the sample statistics. You're actually just going to be given the data. the sample itself. And so one really powerful thing is to be able to use the data and just calculate the p-value under a null hypothesis. So instead of using the sample statistics, we're going to use the sample data directly. And I'm going to show you that there's a much simpler way of calculating p-values than using a t-statistic, using the CDF, and then multiplying it by 2. There's actually a much simpler way. You need to understand how this package works, which is what we've just walked through. But once you understand it, we can just use the package directly. So I'm going to show you how to use it. It'll be one line of code, and then we'll be done. So first off, we're just going to import our stuff. And then second, we're going to load this observational data. So we have a bunch of wait times, and we're going to look at the data. So this is just the data set, a bunch of wait times, and then we have a null hypothesis of 10. We can figure out that the length of the data is 30. But what we can do is just plug in the data into a statistical package that performs the t-test for us. So our null hypothesis is 10. All we need to do is run this line to give us a p-value and a t-statistic. So we have our stats module. We have our t-statistic. This is a one-sample t-test. We plug in the data into the package. So it's a function, it takes in the data, and it takes in the null hypothesis. And then it's just going to perform a t-test and give us a p-value. Okay, so here we have, I changed the numbers a little bit so that the number here is slightly different, but it matches exactly the p-value we found with this package. So no matter which way you do it, you're going to get the same numbers. It's just this way is way simpler. You don't have to go through and calculate the CDF, take the absolute value of the t-stat, plug in the degrees of freedom. This package does all of that for you. And then it will print out for you a p-value, which looks like this. Okay, any questions here? So the rest of your life, unless you take in-class stats hypothesis testing type questions in an exam, you will always use a computer to save you a ton of work to do t-tests. One line of code instead of thinking about running a bunch of stuff. In the background, it's going to do all the work for you, thankfully. I've never done a t-test by hand with data. Never have. Zero. Like literally zero. We always have computers do it. Now you have the tools. So I'm going to ask this of you on your homework. Okay. Any questions here? This is good news. Okay. The only reason I think stats classes are using this by hand approach is to be able to test you on it in class, but there's no reason to really do it anymore. You need to be able to understand the process, but actually doing it by hand is literally never done. Okay, so this should be 2.5, not 2.3. But the basic idea you'll remember is we have this null hypothesis. We center the distribution on the null, and then we just check the area of the tails as extreme as our sample mean. So it looks like this. But I want you to think for a second, so this is our sample mean, and then this is some number that's on the other side of our null hypothesis that's as extreme as our sample mean. So it's 0.85 minus our subtracted from our null hypothesis, which gives us something that's equally as extreme as our sample mean, but just on the other side. And so what we're doing with a two-tail t-test is finding the area under the curve that's more extreme on both sides. I asked you this question earlier, kind of priming this slide, but I want you to think for a second about why we use two tails. Why is it not just this tail? Yeah, Luke.
Because it's strictly like not equal to 10 instead of what if it, like what is the percent that we see something that's greater than 10 or less than 10? So since we need to see like if it's not equal to 10 at all, we need to see like both sides greater than and less than.
Yeah, so it's sort of like if I were to sort of restate this observation, it's like the null hypothesis tells us a distribution, and then we're sampling from it. So we could, in theory, end up under the null hypothesis with something very extreme but much smaller. So it's sort of like going into this with our null hypothesis, we don't know whether the extremeness comes on one side or on the other side. So we need to think about all types of extreme in either direction. Yeah, which is what Luke is saying. What else? Anyone think we should just use one tail? Corin.
Would one tail be if the null hypothesis has to be if there's a greater? Does that have to do with it? Like whether the question is framing as are we expecting to see a greater observed extreme value?
Yeah, so if there's some reason for us to believe that we will not get wait times that are extreme on this side, maybe, like in some cases, we do use one-tail t-tests in those kind of environments where it's like going into it, we would not expect the wait times to be smaller. Yeah.
We can use a single tail if it's like if we have like a approximately normal distribution, we can just multiply that value by 2.
Yeah. So to get a two-tail t-test, we basically multiply the p-value by 2 from the one-tail t-test. What Corin's observing here is like maybe there are some cases where we just would never expect to get smaller values than the null hypothesis. But I will say those kind of environments, even though you were probably taught about one-tail t-tests in your stats class, we just like generally don't use them. And so there are kind of two reasons for this. It's like going into a test under the null hypothesis, we should not come in with any preconceptions. It's like there's this sort of idea of like scientific integrity by allowing the data to follow from our test and not looking at the sample before we run the test. So there's this sort of idea of scientific integrity, allowing the evidence to fall equally, potentially in either direction. And then just from the reasoning we've walked through in the last like 3 weeks of class, like part 3 and now part 4, just the process of how we construct these tests requires us to be equally open to evidence on either side of the null. In every case except rare exceptions, I would say. So two-tail is generally the type of tool we use. But you can think critically about it. Maybe there are some cases where you would want to use a one-tail t-test. Talk to your stats prof about when to use a one-tail t-test. But in general, we're just going to almost always use a two-tail because of this idea. All right. Before we move on, are there any questions here? This is almost an aside. I almost didn't bring this up, but I want you to be thinking critically about how we construct these tests, because you will be required to run some tests on your own and to be thinking about how to construct them for yourself. Okay. So What we've done so far is ask questions about one samples. So single samples, and then we check it against a null hypothesis. And if you're thinking critically about this, let's go back to our test here. If, so our null hypothesis was 10. I'm going to bring up this, this picture here. So our null hypothesis is 10 in this case. What if we were to change the null hypothesis to be, let's say, 9? What's going to happen to our p-value? So this is the picture I want you to have in your head. What's going to happen to the p-value if we change it from 10 to 9? So I'm going to actually copy this. I'm going to ask you this question directly. So how many of you think the p-value in this second one, where we drop the null hypothesis from 10 to 9, how many of you think this number will be greater? How many of you think it will be equal? And how many of you think it will be smaller than this test? So all we're doing, we're not changing anything about the data. We're just changing the question we're asking, the null hypothesis. Do we think, how many of you think the, I'm looking for a raise of hands here. How many of you think the null, the p-value associated with this statistical test will be greater? P-value will go up. Raise your hands high. Remember, you can be wrong. How many of you think the p-value will be smaller? Hands high. And how many of you think the p-value will be the same? I think this same is definitely not right. Throw my loyal front row crew under the bus. Okay, someone want to make the case for why the p-value would be greater. So we move this null hypothesis further away from our sample mean. Why is the p-value going to go up? Someone want to make the case why it gets smaller. Yeah.
Because it's going to be a smaller percent are going to be that extreme if you're moving like that value to the left farther away from the null.
Nice. So it's definitely not staying the same, it's getting smaller. It's a very good explanation. So when we center this distribution on 9 instead of 10, the area under the curve is going to be much smaller. So the distribution will, start here and then drop down, and it will be much lower. So the area under the curve on this one side will be smaller, which means the area on the curve, because it's symmetric, on the other side of the curve will also be smaller. We're going to have to move this equally extreme value to be much smaller. So this p-value will go way down. And let's just test it. So this is a number that's very small. It's like 0.5 zeros followed by 19. So this p-value has gone down. I show this to you to demonstrate that the choice of our null hypothesis matters, which gives us some, this is like a tricky problem when we're thinking about scientific integrity. Like, how do we pick our null hypothesis? We get to pick it when we have one sample. When we have two samples, and we ask a question like this, instead of asking whether it's 10, we ask whether two samples have the same mean. This gives us less flexibility in our null hypothesis, which is a good thing. What we're going to test here, instead of testing whether the mean is equal to some value, we're going to test whether the null hypothesis, the means of two samples are equal to each other. And this gives us one less degree of freedom, sort of less control over our question, which is a very good thing. Precisely for the reason I showed you before. Because if we pick 9 instead of 10, we get a much more extreme answer. Okay, so we're going to ask this question. are two means different from each other? And this is such a common question. This is like one of the most common questions you see in science, any area of science, including economics. So the one we're going to look at today is, are wait times different at different times of the day? So wait times in the morning and the afternoon, are they different? We're going to ask this question. We're going to build the intuition for how we perform this test using the single sample t-test that we've been using. I'm going to show you some other examples at the end, but appointment wait lengths with different doctors, wages across different groups. So some of my students last semester did projects on the gender wage gap. This is a classic example of a t-test. And then treatment effects in experimental settings. So, we just run multiple treatments. We use this in drug trials. Drug trials essentially are t-tests. Lots of examples of t-tests. You check whether two groups are different. So here, this is just a picture of wait times in the morning and the afternoon. Unfortunately, the text size is a little too small, but this says morning and afternoon. And so I've used just a jittered box plot to show the actual distribution of the data in the morning. And on the vertical, we have wait times. And then in the afternoon, we also have wait times. So you can see they look very different. But we want a statistical test to tell us the probability that they would be essentially equal. So probability, we see something this extreme under the assumption that they're equal. Okay, and then here we have, so this is the distribution of the data. And this is the mean wait time. And then we have the standard error constructed using these whiskers. So this gives us some sense of the standard error around our means, our sample means. And you can see a couple of things, right? Like the standard error should be much smaller than the standard deviation or the variability in the raw data, because there's less variability in the sample mean. So these error bars are much smaller than these error bars, simply because we're representing standard errors. Okay. So we have these two data sets, and we're asking whether they're different. What we've done so far is think about how to compare the sample mean to some number. But we have this problem. It's like we're trying to compare. If you're presented with this for the first time, like you hadn't seen a two-tailed t-test before, anyone have any ideas what we might do? We're trying to maybe take this data and turn it into something that we can use with a single sample t-test. Anyone know what we might do? What if instead of thinking about the two samples, we take the difference between their sample means? So what I'm going to show you next is an example of the difference between two sample means. So we're going to repeatedly observe two distributions. We're going to take the difference in the sample means, and then we're just going to plot them. But it's going to be under a certain assumption. So here I've run many samples, and I've taken the difference in their sample means. And I've done this 1,000 times and plotted a histogram. And what I've done is actually drawn from two distributions where the means are equal. And what you can see here is that running many samples with the differences, we see a distribution that's centered on 0. So no matter what the underlying distribution is, if we're taking two samples, we're taking the difference in their means, and we plot the distribution of the difference in their means, we get a distribution of the differences that's centered on 0. It's a mouthful, but you can just see. If the two distributions are equal, the difference is going to be centered on 0. Does this feel intuitive? I'll take that as a yes. The distribution of the differences will be centered on 0 when the two distributions have the same mean. Okay, so this is just a picture of that. But you might be wondering, how do we get the standard error of the distribution of the differences of two sample means? So I just want to walk through a bit of the math. We're not going to do a ton of this math, but I want you to see what it looks like. So for a single sample mean, you remember the standard error is just the standard deviation of the sample data divided by n, and then we take the square root of that thing. So the variance divided by n, take the square root. With the difference in sample means, there's a bunch of math behind the scenes to get this. It's not too complicated. You may have already seen it before. But the standard error of the difference is equal to the square root of the sum of the variances divided by the n. So we take sample 1, take its standard deviation, or its variance, divided by the size of that sample, and then we add it to the same thing for the second sample. And then we just take the square root. Okay, so a couple of observations with this thing. This is how we get the distribution of the t-distribution of the difference in sample means. We have two sources of variation. So if you think about if we have one sample, there's some variation. When we add the two samples together, the variation is going to get larger. So the variation will be larger when we take differences. And if the two samples are identical, then it's just this thing. So if so we would get something that's just essentially square root of 2 larger. But I just want to show you a picture of what this actually looks like. Sometimes the math can get confusing or like you get lost in it, but I want you to get the intuition for what's going on here. We have one sample. So let's say we have two samples. One of them I've shown here. One of the two original samples in blue. When we add the two distributions together, or we take the difference, we're increasing the variability of the distribution. Subtracting the two distributions from each other increases the variability. And so we can see that here. So this is the original one. When we subtract the second one from it, we're just increasing the variability. So this difference is actually more variable than the original, either of the original distributions. Okay, so with a two-sample t-test, typically our null hypothesis is not going to be free for us to choose. It's going to be essentially that the two means are equal to each other. Another way of stating this is that the difference is equal to 0. This is our general null hypothesis in two-sample t-tests. We're going to formalize this and extend this into slopes and relationships and all of this later. But this is the basic idea, that there isn't any difference. There isn't anything going on here. So this is the difference in the means is equal to 0. And so once we're in this environment, we have the distribution of the differences. So we have the null hypothesis, and we have the variability in the differences, right? We just constructed the standard error of the differences. And now we have the null hypothesis, and we also have a sample mean. So our null hypothesis looks like this. It's really just right here at 0. It's basically always going to be at 0 when we do these types of tests. You're not going to have the choice about what your null hypothesis is in general, which is a good thing. And then let's say we observe that the difference between the two sample means is 1.1. So we have a t-distribution. We've constructed the distribution using the standard error from the differences. and we observe this difference in means. We have our null hypothesis, which is where we center the t-distribution, and then we see this green bar. Does this look familiar to anyone? Okay. This should look identical to a one-sample t-test. All we've done here is we've taken two samples, we've taken the difference between them, we've constructed a distribution from that difference, and now we can do exactly everything we've done before for hypothesis testing. It's just the null hypothesis is forced to be 0. So to find the p-values, all we do is find the area under the curve beyond this extreme value. So we need to look at our sample mean and then also the equally extreme value on the other side. So it gives us the two tails. And we know how to do this. Okay. This is the critical insight. Like, this is how we do it. We take this idea of single sample t-tests, and then we just extend it into two by taking the difference. Okay. So this was all under the assumption, with an example showing that we have two samples with equal means. So our sample data is actually centered on 0. But in general, we won't see that. So this is an example where the means in morning and afternoon are not equal. So this is going back to our original example. We had this data. So the means don't look to be equal. And so we need to think about how we quantify the level of surprise that they're different. So all we're going to do is we have sampling distributions for morning and afternoon. And then we're just going to observe one of a bunch of potential sample means for both. So I've just drawn one mean, just happens to be exactly at the middle of both of these distributions. But it's just our observation of wait times in the morning, observations of wait times in the afternoon, and then I've taken the difference. So here you can see just I've run this like 1,000 times and then plotted the difference, as well as the original distributions of the sample means. Any questions about this picture? I've just done the basic thing 1,000 times, both for the individual distributions and for the distribution of the differences. And I have one example, just like one observation that I've labeled with the dashed line. So here we have a sample mean difference of 2.04. So it's like roughly 2 minutes longer in the afternoon, how long you have to wait. Okay, I can't read you right now. Are you tracking? You can say no. It's always my promise to you, I'm watching you, like making sure you're tracking. You let me know, you let me read you if I'm going too fast or like things aren't making sense. Okay, so this is our distribution of the differences. So far, this is all just 1,000 repeated observations, and we're going to look at one particular example, which I've labeled with the vertical dashed line. So next, under the null hypothesis that there's no difference in the means, we center the t-distribution. Remember, we can get the standard error of the differences through that formula I gave you before. We can center the t-distribution on our null hypothesis, which is that the differences are 0. So we have this distribution, which is centered on our null hypothesis, which is 0. So now we're in a world where we can do all the things that we already know how to do, right? We have our observation, which is in green, we have our t-distribution, and we have our null hypothesis. So let's just calculate the area under the curve that's more extreme than our observation. And that looks like this. So we're going to find the equally extreme value, which in this case is on the positive side. And then we want to find the area under the curve, under this curve that's more extreme than these two values. Anyone know what this number is roughly? What's the p-value here? Just by picture, yeah.
Ridiculously small, right?
Yeah, like nearly zero.
Like, one.
Yeah, probably smaller than that. Yeah. This is basically zero. There's basically no area under the curve that's beyond these 2 points. Okay, so nice. So the p-value tells us the difference is more extreme by chance, and this is basically zero. There's no area. So the last thing we're going to do today, or second to last thing, is actually run this type of test. I need you to understand the theory, and I will ask you to tell me about the theory. But a lot of what we're going to do after part 4 is actually just run these models. And in the background, this is precisely what we're doing basically every time. Okay, so let's hop over to a notebook, and we're going to perform a two-tailed t-test. So what I've done here is I have the morning times, and I have the afternoon times. And if you wanted to, you could plot this. So plot this with a vertical scatter and box plot. Let's see if Gemini's just been updated. I don't feel like writing out all this code manually, so if it doesn't, yeah, we'll save that for another time. I don't want to write it out by hand. But so we have all of this data, and all we want to do is essentially test whether these two things are different from each other, which is identical to testing whether the differences is different from zero. This picture here is what I want you to think about when we run two-sample t-tests. We're testing whether the differences are different from zero, which is identical to testing whether the two things are equal. Turns out this is trivially easy to run. I'm going to load the stats module, so from above. This is, scipy.stats. So the scientific Python package, going to find the stats module and then just call it stats. So like my friend in college called me Little Tay, we're just calling this package stats. And then we're going to find within it the module, the function that runs a t-test. And this is independent. So it's the independent two-sample t-test. So we're not making any claims about whether the two samples are similar in any way. We're not making any assumptions about that. I'm going to load the first data set, morning, and then the second one, afternoon. And then we're just going to say that the variances are not equal to each other. So we don't know necessarily that they are. We're just going to run this, and then we're going to get a p-value. And someone who hasn't given me an answer yet, tell me what this p-value means. How do we interpret this? Okay, I'll give you the answer. Forcing my hand. We're like 2 minutes away from the end of class. I have one more thing to do before we go. So, small p-value, which is what we got, we have a surprising difference. Large p-value, it could happen by chance. So essentially we're saying wait times are longer in the afternoon than they are in the morning. We have a tiny p-value, and essentially we're just rejecting the null that they're equal. So it's very unlikely that under the null hypothesis of them being equal, that we get the result that we do. I have one more thing. This is basically just where we're going next. We have gotten to the front porch. We are hands on the door, about to open. the main model that we use in the field. These are this is the ground truth. This is how we run these things. This is the theory for what we're about to do. We're about to start regression. With one sample t-tests, essentially we're testing whether the sample mean is equal to some specific value. With two samples, we're testing equality of means. So it sort of forces our hand into testing that the difference is equal to 0. Next time, we're going to do both of these things with a model that we call regression, which I know some of you have seen before. Two sample t-tests are just incredibly common in every area of science and economics. We test lots of different types of things, differences across different groups. Next time, we're going to extend this into 3 groups, potentially, by introducing this idea of regression. These are all the same model, which is the thing we're going to spend the rest of the semester working with. All right, so I'll send an announcement when homework is posted, potentially today, maybe tomorrow. Welcome back. Nice to see all of you. I'll see you next time.